All right, welcome back. So, locating the center of mass of an extended object by subtraction method. So, if we were to use the center of mass for any kind of symmetry or symmetrical objects, right, such as a square, right? Now, square would have center of mass located as geometric center, which is right at the center. Okay.
Yes, we can.
Oh, I'm not sharing. I know. Oh, thank you. So, all right, there you go. Can you see now?
Yep.
All right, thank you. So, square would have center of mass at its geometric center. Now, if you were to bring this to like a three-dimensional, like a cube, then the center of mass will be inside the square in the center. So, if you were to look at it from all sides, it would be still located at its geometric center. Similarly, a two-dimensional flat circle, right, would have its center of mass at the center of the circle. And if it's a sphere, three-dimensional sphere, it would also be exactly in the center of that sphere, right? Assuming that these materials are made of uniform density, okay? Equilateral triangle, etc., etc. Now, if you have like a rectangle, right, it'd be at the center of this geometric center. So, what if there's a hole cut out of it, right? So, if we had, let's say, a circular disc, right, a plate, and it has certain thickness d, but we cut a hole like so, then how do we actually find the center of mass on that? You know? So to do this, we have to use subtraction method, right? Subtraction method is literally instead of adding other center of masses, you are just subtracting what the center of mass would have been there. Okay? So to figure out the center of mass of each one, right, you would feel okay, the center of mass of a circular plate would be at the geometric center. Okay? So this mass minus the hole, which is basically what the hole is cut out, right? So you take this and then you subtract them and you get exactly the same thing. Okay? You have to assume that it is uniform density. Okay? So with a positive density rho, right, minus the negative density, right, then you're going to get that exact same cutout of the plate. We know rho is equal to, right, mass divided by volume. So if this were made with a uniform density material, and all the material in here is uniform, right, then we can actually calculate what the mass is in terms of rho and volume, right? So you can say mass is equal to rho times the volume of this plate. Now the plate will have volume of, right? Right? Area times the thickness of this plate, right? So area is pi r squared times the thickness d. Now for the big plate, our r is 2r, right? So the volume for this, is, right, pi times 2r quantity squared times the thickness d. Okay? So that's all this. Right? All of this, actually. Okay. Now for the hole, here, this is the hole. The volume for the hole happens to be pi r squared d. Okay? So if we were to solve for the volume of this solid, then our volume for the solid becomes 4 pi r squared d. And the volume for the hole is just pi r squared d. Okay? So if we were to solve for the mass of the solid disk, right? The mass of the solid disk is equal to rho times the volume. So rho times 4 pi r squared d is what the mass of this solid volume would be. And the mass of the hole, right? Mass of the hole would be rho times pi r squared d. Okay? So if we were to find the center of mass of this object, then let's consider this right here to be our 0, 0. All right? So we will put our reference point right at the center, and that's our 0, 0 right there. Okay? Then we can figure out what the x sub cm is. Right? Y, there's a symmetry there, so you know it has to be on the x-axis. So x sub cm is equal to, right, m solid, right, x solid plus m whole x whole. I did not curse, okay? I said x whole. Divide that by, right? Oh, that should be minus. I'm sorry. That should be minus. Subtraction method. Obviously, we're using subtraction method, so it has to be minus. M solid, right? M solid minus the M whole. Okay? So basically, this is what we get. So if we plug in, what is the x of solid? X of solid is 0. So this whole term goes to 0 right here. Minus, right, m whole, which is this, right, rho pi r squared d, times x whole is negative r. Okay? And that's what we got right here. So this is basically 0. So this is 0. Right? So this whole term goes to 0. Right? And then minus m whole, which is this rho pi r squared d, times x whole, right, which is just negative r, because that's in the negative x direction and r distance away. Whole thing divided by mass solid, which is rho pi 4r squared d, minus mass whole, which is rho pi r squared d. So what happens? Well, we could probably factor out a lot of stuff, because we could factor out, well, this becomes positive, right? and this becomes rho cubed, right? So here, rho pi r squared d can be factored out from the top. So my x sub cm is equal to, here, if I factor out this times this is positive, so rho pi r squared d times r, right? You'll see why I did that later. Divide that by, if I factor out the rho pi r squared d from both of this, right, I get rho pi r squared d. Then if I factor that out, what do I get? I get 4 left over here minus 1 left over here. Boom. So this rho pi r squared d can be canceled out to 1. So what do I have left? I have r over 3 left over. That means my x sub cm is just 1/3 r in the positive direction. Okay? So my x sub cm is, if this is 2r, 1r, 2r, 1/3 r will be somewhere around here, of course. I'm just estimating. That's where the center of mass of the whole system would be. Okay? All right. So let's take a look at an example problem. Okay, let's take a look at an example problem. Let's say I have a square plate, right? It's a square plate. And then it's a solid plate with a circular hole, right? With a circular hole cut out with 1 meter radius. Okay? Now, it'd be nice to show where our origin 0, 0 is, you know? I mean, I could put it here. I could put it here. I could even put it here. Or I could even put it somewhere, anywhere in here, anywhere. Even out here, I could put 0, 0. But if you do it correctly, you'll still get the same center of mass somewhere around here, okay? Even though the number may be different for the coordinate system, but the location will be the same. So why make it hard for ourselves when we can make things easier, right? If we make our center of mass location for the plate to be right at the center, and we'll consider that to be our origin, you know, that would make it everything so much easier because I'll get rid of one of them, right? I'll get rid of one of the center of mass at the top. So if I were to sort of like use that symmetry method and then use that as my origin, so I'm going to consider the center of mass of the plate to be my origin. So I'm going to say this right here is my 0, 0, right? Then this is the center of mass of my solid square plate, right? Of course, this would be 1 meter, 2 meters, 3 meters in the positive x direction. This would be 1 meter, 2 meters, 3 meters in the positive y direction. So this location here would be representing 1, 1. Okay? So that would make things a lot easier now. Okay? So again, if I were to think about this being, the solid right here, right? Solid here. So the mass of the solid is equal to, right? Rho times the volume. But what is the volume of this solid? The volume of the solid is equal to, right? Basically 6 squared times the thickness d. Okay? So that comes out to 36d. So the mass of solid becomes 36 rho d is what we get. Now for the volume of this hole, right? The volume of the hole, right, is pi r squared, which is pi times 1 squared, right? So pi times 1 squared times the thickness d. So it's just pi d. So the mass of the hole is equal to, right, just rho times pi d, or pi rho d, right? So now that we have these two masses, we can now focus on concentrating on finding the center of mass, right? So we're going to have to do it two ways. We're going to have to do the x and then y, and you'll see later how x and y will be, symmetrical, right? So we'll get the same answer for both, right? So let's take a look at the center of mass for x direction, the x center of mass, right? So you can simply say r sub x cm is equal to, right, x sub cm, and that is, right, m solid times x solid, right, minus m whole x whole, right, whole thing over m solid minus m whole. Right? So if we work it out, right, my x sub cm is equal to, again, mass of the solid is 36 rho d times x position, center of mass position of the solid is at 0 for my x. So that's 0 minus, right, m whole, which is pi rho d, right, times x position for my hole is 1, positive 1. Okay? Whole thing divided by 36 rho d minus pi rho d. Okay? So it looks like I could factor out like rho d, right? So if I factor that out, this looks like 0. Right? This looks like 0 minus rho d and then I get pi left over at the top. Right? Whole thing over, if I factor out the rho d at the bottom, I get 36 minus pi. Okay? So rho d can cancel out nicely to 1. So what do I get? I get pi over negative pi over 36 minus pi. So what is that? Digitally, I guess. So, I mean, I guess you could leave it like this. This is like a real answer, right? So you could say that this x hat. You could do that. Leave it like that. So that's exact answer. Now let's take a look at r sub cm in the y direction. Right? So here, r sub cm in the y direction, which is y sub cm. Okay? So y sub cm is really just nothing more than, right, m solid y solid minus, right, m whole y whole, right, and then m whole here, and then y, and the m solid here. Pretty much the same thing, except it's y's. Right? So here, my y sub cm is equal to, right? Again, here, mass of solid is 36 rho d, right? Times, what's my y coordinate of my center of mass? It's 0, right? Minus mass whole, right? Which is pi rho d, right? Times y whole is 1. Right? Again, you get 36 rho d minus pi rho d, right? That looks identical to this. Right? That looks identical to this. So you can say now, you can see, due to symmetry, right? You could see that this will go to 0, right? And you can factor out the pi rho d again, right? So rho d, I mean, right? So you're going to get pi here. And if you factor out the rho d on this side, you're going to get 36 minus pi, right? So you get the exact same values here, which is negative pi, right? So this goes to 1. So you're going to get negative pi over 36 minus pi, right? And that will be in y hat. Okay? So you can conclude that my R sub Cm is equal to, right? You can say negative pi over 36 minus pi x hat, right? Minus pi over 36 minus pi y hat meters. So where's that located? It looks like, let's say this is 3 and this is 3. So it's like 3 divided by 33, right? So it's like negative 1/11th, right? Or negative 1/11th. So it's like really close to, so it's around here somewhere, like really, really, really close to. So negative 1/11th, comma, negative 1/11th. Right? So it's like not even 1/10. So it's like very close to the center of mass of the plate. Okay? All right. So now that I showed you how to do that, let's see. Oh, we got one more. Okay. So this is just an explanation. The uses of center of mass. Okay. So according to the net force is equal to ma, the center of mass moves as if it were a particle with a mass at the system. So if we had like an elephant, flying through like, air shot out of a cannon, let's say, right? The elephant's going to have trunk and it's going to have like ears flopping, tails wagging, the whole body with 4 legs, right? And if it's like rotating like this, you could treat the elephant where all the mass of the elephant is located at its center of mass. So you could treat the elephant as a point particle, okay? And that makes it easy to calculate things and estimate where it's going to land and et cetera, okay? So we're simplifying it basically, okay? So the center of mass concept is very useful for solving 2 kinds of problems. One is determining the motion of the rigid body by using simple, right, F equals ma method, because you're treating everything as a particle, okay? 2, you could simplify problem solving the motion of 2 or more particles by center of mass frame of reference. So if you have more than one object, let's say you have a cluster of objects, right, traveling as one unit, then you could figure the center of mass of that cluster and then think about it as one particle. So if you were to like think about like a galaxy, right? Spiral galaxy, and then you're comparing that to another spiral galaxy, right? You could treat each galaxy as a point particle of all the masses located at the central supermassive black hole, right, as a particle, and then you could actually calculate the gravitational attractions and et cetera, et cetera, et cetera. All right. So the center of mass concept really helps you simplify a lot of complex systems into a particle. And that's why it's useful for using center of mass. All right. All right. So if you were to see like a tomahawk being thrown, or maybe even a diver, right, going through the air, doing somersaults and stuff, but if you follow the center of mass of the tomahawk or the diver, you'll see that center of mass will follow that perfect trajectory, right? As though the whole body is moving in that center of mass position. All right? So that's pretty much what center of mass is used for. All right. Now, I'm going to give you some time to work on this. So see if you can work on this problem and the rest of it, if you can. All right. And then we will meet Friday, and then we'll go over this. Okay, we'll go over this, and then we will, I guess, do the quiz. All right. All right. So start this now. Got 10 minutes. Now, where would you put your 0, comma 0 to make it easy? I mean, would you put it here or here? I would put 0, comma 0 right here as my coordinate system. Then you can use this symmetry of y direction along the x-axis to eliminate, this part. Then you know your center of mass has to be on the x-axis. Okay, so I would put it right here in the center.